guys, we are starting chapter 5 today. Chapter 5 is going to be the last chapter that we cover in Algebra 2. Yes? All right. All right, guys. Now, what we're talking about in this last chapter is rational exponents and radical functions. Radicals are square roots, cubed roots, fourth roots, and rational exponents, so fractional exponents. That is what we're looking at in chapter 5. Now, the first thing we want to see, and this is at the top of your note sheets, which is greater, the square root of 64 or the cubed root of 64? Because the square root of 64 is 8, and we're saying that one's bigger. What is the cubed root? Because the square root of 64 is going to be bigger than the cubed root. Because when we say square root, we're looking for what number times itself? 8 times 8 is 64. When we talk about the cubed root, we're looking for what number times itself? 3 times is 64, and that'd be 4. So the square root of 64 is bigger than the cubed root of 64. And this is some of what we're going to be looking at. Now, this first thing here, previously you learned the nth root can be represented as this here for any real number. So the nth root of a is equal to a to the 1 over n. And we can expand upon this a little bit. Our radical. Our nth root of a to the x is equal to a to the x over n. Nth root of a to the x is equal to a to the x over n. So the exponent inside, attached to our a, the number inside the radical, goes on top of the fraction. And up to this point, especially in Algebra 1, we just had a. We had it as a first power, so it's 1 on top. The root goes on bottom. So our root, our index, goes on bottom. The exponent inside goes on top. And it could be written in a different order because this is also, we could say that the nth root of a to the x is equal to a to the x over n as well. And there's properties of radicals that get us from there to there. But this is helpful, this is nice, and this actually explains a good bit. Because for the longest time, we've said that the square root of a squared is a. The square root and square cancel out. And that's about as far as we did, especially when we first introduced this. Now, this property here states, well, our index is 2. If I wrote this as a fractional exponent, our index, the number outside goes on bottom, which is 2. This 2 goes on bottom. The 2 inside goes on top. So we have a to the 2 over 2, which is a to the first, yes? So just be a. This is why if the index and the number inside, its exponent, are the same, they cancel out. Because no matter what the exponent is in index, we could say the 81st root of a to the 81 first is just a to the 81 over 81, which is just a. That's why that simplifies out. Now, we don't introduce that originally, especially when we first introduced square roots, cubed roots, fourth roots, because for most, especially in 8th grade, I think you're doing well enough just trying to comprehend what a radical is, let alone what a rational exponent. So, we introduce this a little bit later, and this really gives us a good understanding of why square roots and squares simplify out. More specifically, they're inverses of each other. They undo each other. The same with our exponents and logarithms. When we have exponentials and logarithms are inverses. Radicals that are exponents undo each other. Now, the first one you're looking at is this here. Well, yes, these are indeed the same. Because our square root of 9, well, 1, well, not 1, 2, and 1. So this would indeed be 9 to the 1/2. Square root of 2 is equal to 2 to the 1/2. Yeah, because if we rewrote the square root of 2, the index is understood to be 2. The exponent attached to it is 1, so we get 2 to the 1/2. And there's not a whole lot to this, and I probably said it last year, I'm thinking of just taking this part out, because there's a whole deal with this that y'all would go and use calculators and approximate and work through. This here, to get the answers, the cubed root of 8 would be 8 to the 1/3, which is indeed what it's equal to. Yeah, there's not much to this page. Not really. Evaluate each expression. So if we want to evaluate these, we take it part at a time. Because we can look at the square root of 5 and then cube it. Because the square root of 5, I can say second square root of 5 is this here, or 2.236067978, and continues on. But then we're taking that to the third power. $11.18033.99. Or I could have just typed it in as what? Parentheses, second square root of 5 to the third is 11.1803. Questions on this here? Well, we can also do the fourth root of 4 squared. We'll do it both ways. I'll do the first way here on the calculator. The fourth root of 4 is 1.41423562, continuing on, yes? And then we're going to put it to the second power, which is 2. Which is 2. Now this seems odd that it would work that way, yes? Well, let's look at it. So we said inside, fourth root of 4 here. If we wrote that as a base to a power, that'd be 4 to the 1/4. We're good with saying that there, 4 to the 1/4. Index goes on bottom, exponent goes on top. Index, the number inside the radical, that little v, goes on bottom. Since the exponent attached to the 4 is 1, it goes on top. 4 on bottom, its exponent goes on top. So we comfortable with saying that the fourth root of 4 is the same as 4 to the 1/4. Yes? Powers of powers do what? They multiply. So our 4 to the 1/4 squared, well, our 1/4 and square, that 1/4 and 2 will multiply together. What is 1/4 times 2? That would be 1. Yeah. So we're back to 4 to the 1/2. Yes? Now we're not as used to seeing 4 to the 1/2, so let's put it back as a radical. The number inside would be 4, because that's the base, yes? Its exponent number on top would be 1. 4 to the first or just 4, yes? Our index is 2. So 4 to the 1/2 is the same as saying the square root of 4. And the square root of 4 is 2. That's why that one worked out. The previous one, rewriting 5 in cube, did not give us anything helpful. It's really just saying we're taking the square root of 125. But radicals and powers. Cubed root of 9 squared. And in some of the ways they'll say that we can break it down into our parts. But the cubed root of 9 squared is 4.326748711. 4.327 lot, some of it will be. Some of it will be just evaluating, because if we're just evaluating what's given, we're going to plug it in and let it do the work for us. There will be some, especially when we get to solving, we're going to leave it in radical form. Because here, if we wanted to, we could change this into rational form. Because this here would be 9 to the 1/3. Exponent inside goes on top. Index, the number in the v, goes on bottom. So the cubed root of 9 is the same as 9 to the 1/3. And if we apply that power to it, this is the same as 9 to the 2/3. And we could check that. Because we have this here, 9 to the 2/3 is the exact same thing as what we got previous. So in some ways, this is nice to know, because it's sometimes easier to type in 9 to the 2/3 than it is to type in the cubed root of 9 squared. Questions on this here? Well, I'm going to move on to these here, because for the most part, we end up just typing these in. Some of it is getting us used to converting from one to the other, but for the most part, we get used to typing them in, because 8 to the 2/3, if we wrote this in radical form, the number inside would be 8. What would its exponent be? 2, because the exponent's the number on top. 2, and the index is 3. Number on bottom of the fraction goes in the index, the v, and the number on top is the exponent attached to the number. So we have the cubed root of 8 squared. Now at this point, either way we type it in, 8 to the 2/3 is 4, or we could say the cubed root of 8 squared is still 4. We get the same answer. Six to the 5/2. If we wrote this as a radical, the number inside would be 6. Well, the outside, the index would be 2, and the power attached to the 6 would be 5. So we'll have the square root of 6 to the 5th. Now, this is the same. Square root, the 2 is understood. We don't have to write the 2 in the index, the number in that little v, if it's 2. So when we type it in, we can say second square root 6 to the 5th is this here, or 6 to the 5/2. We get the exact same thing. 88 point. Questions on this here? We're ready for what's next. So for these here, let's convert them to radicals. So 12 to the 3/4. Number inside would be 12. Its exponent would be 3, and the index would be 4. Now the way we write it really doesn't matter, especially if you start seeing this. You could immediately put the index first, number, power. Just go left to right. Now at this point here, we can plug it into the calculator, we get our answer. Questions on this here? 10 to the 3/2 in radical form. 10 to the 3rd. And our index, our number in the v, would be 2. Now since it's 2, we don't necessarily have to write it. It's not wrong to write it, but it's understood. So on the graphing calculator, if you hit math, it'll take it a second for this one to load. If you hit the math button, if you look down on the list, there's one with a 3 in the index, and the one below it is X instead of a 3. Either one of those will work, because if you wanted a 4th root, you could select the one with 3, cursor over, change the 3 to a 4, 5, 6, 7, whatever you want. Or the x, you can replace it with the number you want. Questions on this here? Let's look at this. Evaluate each expression without using a calculator. Because we've seen some already that worked nicely, gave us a nice number. Those we can do with or without a calculator. However, say the last two we looked at, those, even though we didn't look at the number, those worked out to be decimals. And it is possible to do them without a calculator, they're just tedious. And it's a lot of calculations. Now the first one we're looking at is this one here, 4 to the 3/2. Let's write it as a radical. So we can say that this is the square root of 4 to the 3rd, yes? There's two different ways we can go from here. We could take the square root of the 4 first, and then put it to the 3rd power, or take the 3rd power of 4, and go from there. Yes. We can rewrite it as this here. Now, how we got here, and I can write this out to the side so we can see it, really all we're saying is that this is 4 to the 1/2 to the 3rd. Powers of powers multiply, yes? So 3 times 1/2 or 1/2 times 3, go either way. So sometimes it just depends on how we want to look at it. Because if we look at it here, it would indeed be the square root of 4 to the 3rd. Well, what's the square root of 4? So we're saying 2 to the 3rd power is. So 4 to the 3/2 is 8. 64. Yeah. Oh no, I'm thinking too hard. Because if we did it the way we had here, I'm going to bring this down. The cubed root of 4 is 64, and the square root of 64 is 8. So it's just how we want to break it down, how we want to simplify it. Questions on this here? And a lot of these, it's going to be easier, just take the square root of a number, then apply the power. So knowing that with this next one, we can do a similar thing. We can split this fractional exponent up. We can have 32 to the 1/5 to the 4th. (32 to the 1/5) would be the same as the 5th root of 32 to the 4th. If y'all had to take a guess, what do you think the 5th root of 32 is going to be? My guess would be 2. Because we're looking for a number times itself how many times? 5. Because 6 times 6 is 36, yes? Okay, well, we kind of cleared it. 4 to the 3rd is 64. I will tell you this, 3 to the 4th is 81. So our best hope of this simplifying is probably 2. 32, 2 is 16. And do it one more time, we do get 32. So the 5th root of 32 is 2. Almost. 16. Because our 2 to the 3rd is 8. We just need one more. And that's it. Questions on this here? Practical application of this, not a whole lot. But it is giving us a way to try to break something down into parts that make sense and then put them back together. (625 to the 3/4) We can say this is 625 to the 1/4 to the 3rd. if you had to take a guess, 625 to the 1/4, what times itself 4 times would give us 625? Right, at 5, I'd be wanting something with a 5, because most likely if we're multiplying two things or itself by itself continuously, and it ends in 5, we would hope it would be 5. Because 5 times 5 is 25. Times 5 is 5, carry the 2, 10, 12. So 625 to the 1/4 is indeed 5. Now 5 to the 3rd. $125. So we've had 3 so far, yes? Now the fractional exponent that we had, was it less than 1 or greater than 1? Because this is less than, yes? And what's happened to the final number? Has it gotten bigger or smaller? Smaller, yes? Does that make sense? Because what would 625, this is a side note, you don't have to write it, to the first be? So it gets us back the same number, yes? I'm not going to use 625 again. Let's say 3. If I put it to the second power, it would be 9. Because when the exponent's bigger than 1, the number's getting bigger, yes? So if the exponent was between 0 and 1, we would expect it to get smaller than what we started with. That makes sense. So I say that less as a rule that we can use, but it's a good check. Because if, for the last one, 625 to the 3/4, if I got, for some reason, 1,298, I know it's probably not right. Because the exponent's less than 1, so our answer should be smaller than what we started with, not getting bigger. Let's look at the next one, 49 to the 3/2. Well, the exponent is bigger than 1, yes? So we should expect our final answer to be bigger than, well, 49, yes? Because we're starting out with 49 to the 3/2, greater than 1, so our final answer should be bigger than it. As we did on the last one, we have 49 to the 1/2 to the 3rd. Well, I realize I didn't write it out for the last one, but yes, it would be 7, because our 49 to the 1/2 is the square root of 49. I just realized I didn't do the 4th root on the previous. And yes, square root of 49 is indeed 7. I think 49 times 7, 3 carry the 6, 343. Yeah. Questions on these here? Calculator can do these just nicely. But again, some of this here, especially with logarithms and these different methods and proof, which seem, for lack of a better term, archaic, they don't work anymore, there's no real reason for it. They did have a purpose and they did have a use when we did. It's just our technology has gotten to a point where we don't really need it because it can do the calculations for us. Because if we didn't have it, calculating 49 to the 3/2, we would need something like this here to really work it out and simplify it. Does that make sense? Logarithms. This is kind of a side note tangent because I meant to say this then. We saw that all the numbers were not nice, yes? And you could calculate it, and they did those. They would give you tables. You had printouts, massive printouts of these tables of logarithmic functions, but again, there's only so much you can put on a page or how many pages you can put together. So we had ways to get those. Because they would give you logarithms of base 10 of 1 through 100. As long as you can get the number between 1 and 100 as a whole number, not a decimal, then we could solve it. So we had methods to get there. And then you could just reference the table and go from there. That's why trigonometry is a subject, because we needed ways to evaluate sine, cosine, tangent, and be pretty accurate with it. we have those there. But, side note, nth root. Nth roots. We're taking nth roots. So we have this first, we have it to start with. And this is when we take the nth root of both sides. Not so much when we're given it immediately, but if we're trying to find the nth root of a number, we're taking the nth root of both sides. We'll do when n is even. Second, we'll look at when n is an odd number. So what that means is if we take a radical here, n of a. So when this n is odd, we don't look at 1 because having 1 as an index doesn't mean anything. So we're looking at cubed root. So when n is 3, 5, 7, 9, 13, 15 going on, we have 3 cases that show up. If a is less than 0, if the number inside of it is less than 0, we have exactly 1 real root. We got that, yes? Now if a is 0, number inside it 0, we're taking the cubed root of 0. We have 1 real root, and it works out that it is 0. Okay, we got that straight so far, yes? We ready for the last one? If the number inside is positive, we have exactly 1 real root. And the reason for this is, again, no matter how many times we multiply a number by itself an odd number of times, we get that number back. So 8. So if I took the cubed root of 8, well, that's just the cubed root of 2 to the third, which is 2. Because 2 times 2 times 2 is 8. We feel good with that, yes? If I told you we wanted to take the cubed root of negative 8, well, what would that be? Negative 2. Because negative 2 times negative 2. Negative times a negative is a positive, yes? And our 2 times 2 gives us 4, positive 4. Let's times it by negative 2. So 4 times negative 2 is negative 8. We get the negative back. That's why the top one works. The bottom one makes sense, and I can multiply 0 by itself as many times as I want, and I still get 0. 0 is neither positive, negative, odd, or even. It's just 0. So if the number inside's an odd, we get 1 real root, and we can just take that. Both calculators are fine with it. Okay? Now, we're going to look at when the root is even, because it gets a little odd. Now, if a is greater than 0, if the number inside the radical is positive, and we take an even root of it, we have 2 real roots. We have the plus or minus. We remember doing this with square roots. We take the square root of both sides. Square root of 9 is 3, but it's also negative 3. We have the positive and negative case because of exponents. So if a is positive, if that number is positive and we're taking an even root, we have 2 solutions. We have to add the plus or minus. If a is 0, we have 1 real root, and it's just 0. Kind of works out nicely on both. And if a is less than 0, we have no real nth roots. And it's been a while since we did this, and this is the same as if we said the square root of negative 4. Is there a solution to this? Well, yes. It would be plus or minus 2i. But is I a real number? No. And again, sometimes you have to pay attention to what they're asking for, because we're wanting here to find what? The real nth roots. There is a root for it, but it's not real. Does that make sense? So there is a solution for it, but since it's asking for the real solutions, the real roots, it doesn't have them. It only has imaginary. It has complex roots. So if it's asking for the real roots, well, they're not any. I can't tell you what's not there, but we can have it for 0 and positive numbers. So if we look at these here, we're wanting to find the indicated root. We're taking the root of the number given. And here, this is our nth root of a. So for our first one here, we're taking the third root of negative 216. is less than 0. And our root is odd, yes? So there are 3 cases. We had it in the chart before. It could be that we have 1 real root, or 1 real root, or 1 real root. Because when the index, the root is odd, that's all we have. We have 1 real root, no matter what a is. So we're looking for the third root of negative 216. Well, I can tell you it's going to be negative. With odd indexes, if it starts out negative, it's going to finish negative. And it is negative 6. 30xs, 3 second x root negative 216 is negative 6. We get a factor treat it, and saw that we get 6 times itself 3 times. Different ways we can get there. Next one we have our radical. The number inside would be, and the number outside is 4. So we're looking for what number times itself 4 times is 81. Now, I did, incidentally. I didn't realize I was going to show up. But the index is even, yes? So we have 1 of 3 cases. We either have no real roots, 1 real root, or 2. We have none if the number inside is negative. We have 1 if the number inside is 0. And if the number inside is positive, we have 2. Since it is positive, we have 2. We have plus or minus, the positive negative case. And the fourth root of 81 is, incidentally, 3. Because 81, the square root of 81 is 9. 9 and 9, we can break 9 down to 3 and 3. So we have plus or minus 3. Questions on this here? N is 4, A is 16. So 4, 16. 4 is even, our root is even, so we have none, 1, or 2. Since the number inside is positive, we have how many? 2, plus or minus. It is indeed 2. Yeah, 2 is the only one that we can actually take the 4th power, put the 4th power 2, and be less than 50. 2 and 3. Because 2 to the 4th is 16. 3 to the 4th is 81. Once we hit 4, we're over 2 digits. We good with number 1. Number 2. The number inside is negative 49. It is indeed. No real. Our index is 2. We don't have to write it if we don't want to. And again, because the number inside is less than 0, this is no real. Or not solution. Yes. No real int or no real root. I've gotten in a habit, I think like most of y'all, to put solution, but we're not solving for anything. Just int. Yeah, nth root. It's just a root. Because we like to use variables to especially express something going out indefinitely. So when we talk about nth root of something is this here. So we're defining it by any value of n that you could possibly conceive of. Because if we try to specifically stick to number values, we have to prove it for everything. So we use variables as a way to prove something to a higher degree. Questions on this here? And part of the reason we do that is especially, we covered this in geometry. The number of cases we need to disprove something is 1. But to prove it, you need to prove it for all. So we use variables. N is 3, A is negative 125. So we have 1 real root. Yep. Because it's odd, we have 1 real root, no matter what the number is. It would be negative 5. And the last one's the fifth root of 243. Since the root is odd, there's just one, and it's 3. Because if the index, the root, is odd, we have one real solution no matter what the number is. If it's even, we have 0 or no real nth roots if it's negative, number inside, 1 if it's 0, and 2 if it's greater than 1, or greater than 0. But that's it. 5 through 16. Yes. Okay. Now, tomorrow we will be finishing up 5.1 with radicals, going over these, especially some of these properties, especially looking at some variables. We'll start 5.2 Wednesday, talking about properties of exponents, continued up to Thursday. Friday, operations, looking at how to add, subtract these here. Unfortunately, fortunately, no matter, just depending on how you want to look at it, I will not be here Friday. So I do have it set up. I will have the lesson, everything ready to go for y'all. And I do have the note sheets, okay? Unlike last time, there's not multiple videos. It'll be the one. I'll have it queued up, ready to go at the start of the day, so you'll watch it and go through that there. I don't like having to do that, but as y'all know, we are wrapping up the end of the year. And I want to make sure we get through radicals, because this does show up for those of you who are going to take college algebra. Radicals and solving does show up again. So I want to make sure we get to it. You've seen it, and we're good to go from there. Yes?
There's zeros